In this example, there's a sinusoidal wave. It's traveling in the positive x direction. It's traveling to the right. It has an amplitude of 15 centimeters, a wavelength of 40 centimeters, and a frequency of 8 hertz. We know that at time equals 0 and x equals 0, the position of the wave is 15 centimeters. First thing we're asked to find is what is the angular wave number k. So why don't we start by making a list of the things that were given. The amplitude is 15 centimeters. The wavelength lambda is 40 centimeters. Let's write that one in meters, 0.400 meters. The frequency is 8 hertz. And the height of the wave, the vertical position, d, at time 0, position 0, is equal to the amplitude, 15 centimeters. So part A asks what's the angular wave number. We remember that wave number is 2 pi divided by the wavelength lambda. So we have 2 pi divided by 40 centimeters to get an angular wave number of 15.7 radians per meter. Next, period t. We know that the period t is 1 divided by the frequency. So 1 over f is 1 over 8 hertz, or seconds to the minus 1. That's 0.125 seconds for the period. The angular frequency omega is equal to 2 pi times the frequency, so 2 pi times 8 hertz gives us an angular frequency of 50.3 radians. So there's our angular frequency. Last, we want wave speed. There's two ways to calculate it. We can do omega times k, or we can do f times lambda. Since f and lambda are given, let's use those two guys. So 8 hertz, or seconds to the minus 1, times 0.400 meters gives us a wave speed of 3.20 meters per second. So there's part A answered. Next, we're asked to find the phase constant phi naught and write a general expression for the wave function. And the wave function means the vertical position of the wave as a function of horizontal position and time. So part B, we're asked to find phi naught. So let's write down what we know. The general equation for the wave is that d is equal to the amplitude times sine of kx. It's a rightward moving wave, so it's kx minus omega t plus phi naught. Let's put in what we know. If x is 0 and t is 0, d is 15 centimeters. A is 15 centimeters. So then we have times sine of kx, so k times 0, minus omega times t, omega times 0, plus phi naught. So that's equal to 15 centimeters times sine of phi naught. So let's divide both sides by 15. 15 over 15 is 1. 15 over 15 is 1. 1 equals sine of phi naught. So then phi naught is the inverse sine of 1. Make sure you remember that when you're doing work here, we're working in radians, so your calculator has to be radians mode. The inverse sine of 1 is pi over 2. So if we just want to double check this against the velocity when we look at the graph, we see on the graph at x equals 0 and t equals 0, the graph is flat. So right here, if we were to take the slope, that would give us the speed. If it's flat, it means the slope is 0, the speed would be 0. And that makes sense because right here is where it turns around. It goes from moving up to moving down. So the transverse velocity would be the derivative of this equation, minus a omega cosine kx minus omega t plus phi naught. At 0 and 0, v of t is minus a times omega times cosine of k times 0 minus omega times 0 plus phi naught pi over 2. So that's cos of pi over 2, which is 0 as expected. So we're good with that check. And now we finish by writing the general expression for the wave function. So d of x and t is equal to the amplitude, 15 centimeters, times sine of k, which was 15.7, times x, minus, because the wave moves right, omega, which was 50.3, t plus our phase constant pi over 2. And there's that problem figured out.